Well, I think it's time for the second meeting in this multimodal interaction course, and this is one of those lecture type meetings, quite similar to the previous one. So I will be talking about speech-based and spoken interaction this time, and what is speech like as an interaction modality, and various aspects related to that. Perhaps you have already, hopefully, had a look at the material in the Moodle, and do ask me whenever there is something you want to have clarifications or whatever. So there are different aspects that this topic will be looked from. First, some generic topics, then what kind of speech applications there are, and then a little bit deeper into the technology related to speech, speech recognition, speech synthesis in particular, and some other components are briefly mentioned in the section before that, and then into the actual interaction and how we can manage that interaction. Built quite a lot from the dialogue style of interaction, but I try to mention different kinds of styles to use speech as well. So, why we would want to use speech in human technology interaction? This is something that has been featured in, for example, science fiction, of course, for a long time, and some people have seen it like speech is the most natural way for us human beings to communicate with each other, so it would be the best way for human-computer interaction as well. This is perhaps quite naive way of looking at it, and we have found lots of other ways to interact with technology, so perhaps it's not the ultimate goal to have the speech-based dialogue with the computers in every situation, but there are still many cases where we would and probably will increasingly have speech. One of the reasons we want that is because speech is natural. For most of us, speech is something we do all the time. We talk to other people, and we know how to use language. We spend years in our early life learning to speak, and why not take benefit of all this naturalness? Speech can also be a very efficient way. Basically, everybody can speak faster than they can type, for example. So speech is, from a very naive perspective, the most efficient way to input text or language into the computer. Because if there is lots of errors, that may make it much slower, because then the error correction cost overcomes or takes away all the benefits we get from the initial fast speed. But it can be really efficient. Speech can also be very expressive. This extends to natural languages in general. So natural languages are these languages we speak, and well, sign languages are as well are natural languages. They are very powerful in expressing different kinds of things. And very flexible. We can express lots and lots of different kinds of things as compared to, for example, graphical user interface, where you can basically do whatever has been built into the graphical user interface, but then you are fixed into that set. And then if you need to do something else, it can be get quite tedious. Speech can increase the bandwidth of the human-technology interaction, and especially in the multimodal interaction. So you might be able to do, for example, manual input at the same time and use speech. As for example, in cars, you might be driving the car using your hands and feet to drive the car, but you can still speak at the same time to control some media system, for example. So we can use more bandwidth. Some people like speech. It's quite popular. Some people are naturally very language-oriented people and, for example, do problem solving by talking about the problems and talking about the issues, and that can help them think. Some other people are more visually oriented and so on. And then one very good reason why speech is often used is that it leaves these kinds of links into the increased bandwidth hands busy and eyes busy situations. So if you need to be paying attention, for example, when you're driving a car, you should be paying attention to what's happening outside the car in the traffic. And your hands are tied into the, or should be tied into the controls. Of course, lots of people nowadays do use their mobile phone and keep on texting, and their hands and eyes are somewhere where they shouldn't be. So in these cases, for example, speech is potentially more safe. And then there are these situations like, for example, doctors in the operating room when they are doing some surgery, for hygiene reasons, they are not allowed to touch mice or keyboards or something because there might be some bacteria there. So in those cases, their hands can stay free. And one case which we might have increasing in the future, for example, in the kitchen when you are cooking and your hands are dirty, you don't want to be touching your mouse with the same hand that you have been just working on some dough or something like that. Of course, there are restrictions why we may not want to use speech in all situations. As an output, speech is slow. So as an input, it's fast. You can, most of you, I think, can speak faster than you can type. But at the same time, most of you can read faster than you can listen to somebody speaking to you, even if that person tries to speak very fast. And it's also serial output, so everything that is said, it must be said one word after another, even no matter how fast you speak. On visual display, you can have lots of information visible at the same time, but speech, you have to put things one after another. And then speech is temporary. When I say something right now, it creates these vibrations in the air, and then it kind of disappears. Only place where it stays are this recording, which this time hopefully works, and your memory. So it doesn't stay there. When you put something on screen or print it on paper, it stays there, but speech just disappears. Then it's also public. If I'm talking out loud to you, everybody can hear it. Maybe some people in the corridors can even hear it. So you don't want to use speech if there is some privacy critical information, for example, used. And most speech interfaces don't allow you to just freely speak and say anything. You must some extent know what you can say to the system, know some sort of commands and keywords, and so there is this learning effort which, well, graphical user interfaces, for example, they display more, show you what are the options. You don't have to remember, you can go and try out, but with speech, it's kind of same as with command line interfaces. You have to learn what are the possibilities. And then when there is interaction, especially if it's speech only, then there is these issues that must be handled, like turn taking. In natural dialogue, when I'm speaking with somebody, we all the time use lots of different methods to communicate that I'm still speaking, you shouldn't start speaking yet. And then when I'm finishing my turn, like my tone of voice goes down a little bit, and I do little gestures indicating that, okay, now it's your turn to start speaking. And modeling this into human-computer interaction is very challenging. And yeah, it's even hard to, of course, we interrupt each other when we are talking to each other, and modeling this can be quite challenging. And then, as said, when there are errors, computer misunderstands me, or I say something I didn't want to, that needs to be corrected, and that can be slow in speech-based interaction. And yeah, then there are these technical limitations. Usually you will use synthesized speech, which I will have to talk more later. That has been improving over the years more and more, but still, especially when you have long text, it doesn't quite sound as natural as human speaking. And because of that, it tends to require more cognitive load from the listener. And speech recognition can make mistakes, mishear words, and so on, more than people maybe on, well, depending on the situation. In some cases, it actually has been better than human beings, but those have been kind of extreme cases with some particular type of noise in the background or something like that. And yeah, when it makes mistakes, those mistakes must be corrected usually, and that takes time and interaction cost. And then the computer, when it's listening to your speech, it always has, as I will explain, some sort of language model. It doesn't understand everything that the human beings use, every word. Of course, none of us human beings understand every word that there is in the language, because they're just almost endless, those languages. But computers have some sort of limited languages, and they can be words that they don't know, or sentence structures which they don't understand, and so on. So if we now go to the speech-based applications, there is one categorization, and this is rather random, but it's one kind of categorization, kind of reminding what kind of interactions we can have with speech. Kind of traditional one, and this material very much builds on this dialogue style interaction, which is not so common nowadays as it was kind of the standard speech interface solution earlier. So dialogue systems where you speak to the computer, and then computer speaks back, and it kind of models interaction you have with other people. These were earlier often telephone based, so you phone somewhere and then you could talk to the computer in the other end. In US they are still, and it's the area where they are most common and have been most common. In Finland, for example, we only had a couple of these. Area where this dialogue style of interaction is nowadays most common is perhaps these personal assistants. Apple Siri is one type of this, Microsoft has this Cortana and so on. So they can do some kind of dialogue with you. Second type is dictation type information entry. So you speak and the computer recognizes what you say, and that is used to enter information. So of course you have these dictation systems where you can just dictate what you would normally type, create documents and so on. But most common one is probably this voice search, so searching by voice. Google Voice Search is readily available both in Android devices and in the web interface, and I think I quickly showed you example of that. If you haven't experimented with it, I recommend try that out. Then we have multilingual applications. Translation systems is something that's coming, so you already have some of these services. You can speak and then it translates that to another language and speaks it out in that another language. Of course, very challenging problem, but reasonable progress has been made in that area. But on the other hand, we can have applications with multilingual content, and this multilinguality is a little bit challenging. For example, if you are using navigation systems in cars, they often have problems with Well, especially if you are using the system in one language and then you are traveling in a country where all the place names and street names and so on are in another language. And of course, there are countries which mix, like Switzerland has 4 official languages and so on. So the navigation system should be able to pronounce all of them and so on. Then multimodal interaction and multimodal applications, but are kind of the core of this course, but won't be so much topic of this lecture. Audiovisual speech synthesis, which I will show one example quickly in the end, this kind of talking head. So you have animated 3D character which also speaks. Multimodal information kiosk where you might use speech and touch gestures, for example. Pervasive applications, this kind of ubiquitous computing, ambient intelligence. One good recent example is this Amazon's Echo and Alexa thing. Alexa is the software part which you talk to and it talks back to you, and Echo is the hardware which sits in your home, and you can talk to it and ask it to, well, you can connect it to the different hardware. It can control lights and it can order you stuff from Amazon and do reminders and play music and so on. And then there are special user groups for speech, especially disabled users, visually disabled. So people with low vision and blind people, of course, they use text to speech, so the computer speaks to them. That we can replace visual display or help support the visual display. Of course, with motor impairments, if you cannot type for one reason or another, using speech can be, if not always efficient, but if it's the only way you can type in text into a computer, you probably see value there. And then there's potential in other areas, like maybe with elderly people, low literate people, and so on. And finally, a couple of categories. Cars, as said, have speech interfaces for the reasons mentioned. Pretty much every big manufacturer now allows some sort of speech interfaces. And educational applications, especially computer-aided language learning, is something where speech interfaces or speech technology can be used and is increasingly used. Here are then a couple of kind of contrasting things built under these titles of conventional applications, traditional ones which we used to have, and then novel applications which we increasingly are having. Just to give you an idea of what kind of aspects there are and where we might be going. Traditional dialogue is between single user and a single computer, and increasingly we have the technology everywhere, and we might be having multiple users and multiple computers. For example, there are meeting room systems which analyze all the time who is speaking and what they are saying to some extent, and make things happen. So that is example of multiple users using a single system at the same time. Of course, they aren't explicitly using, they are just talking to each other, but the computer collects the information. And yeah, you might be using multiple computers, starting with your Amazon Echo at your home and continuing the interaction with your mobile phone on the go. Traditionally, we have desktop systems and telephone. Now it's office, home, mobile settings. Earlier, the dialogue was usually very strict. You bought a ticket to a train, you told where you're going from where to when, tap, 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 step by step, and then you got the ticket. In the future, more open-ended things can evolve as they go. Traditionally, we have more like active user, but now we also have these proactive computers which can do things actively by themselves. Dialogue control, which I will talk about later. It was like a single component. This is the dialogue control module in our software earlier, and now it's more distributed when multiple systems are talking to each other and so on. And earlier the systems were pretty much unimodal speech only, both ways. Increasingly we have multimodal, different modalities involved. Fusion we will talk much later. There it could be like sequential, you speak now, then you do something else. Now increasingly we can use different modalities at the same time and use them flexibly. Earlier speech, text, graphics, now also haptics, gestures, and increasingly using contextual information so that the systems are smart and can react to the things. You don't have to tell everything. From one language to multiple languages. And early on, the idea was often that, okay, we are modeling what the dialogue between two people are, and we try to replace one of those people with a computer. And as new technologies and new possibilities become available, more and more novel ways of interacting have become available. Efficiency as user satisfaction, of course, are still important, but nowadays also things like privacy and context awareness and unobstructiveness can be equally important. And earlier systems are very explicit, some database where the information came from, and nowadays we have more sensors in the environments and different kind of data sources are fused together and so on. So then if we look at what kind of technology we need to create this kind of a speech-based dialogue between human and computer. And this is the picture you see is very traditional spoken dialogue system architecture, but it's still usable if we think about other kinds of interactions, because lots of these technologies need to be included there. So we have user on one end, then we have some sort of input-output device, microphone and speakers, or a telephone, or mobile phone or something. This captures the user speech, and then it goes to the speech recognition component, which turns the sound basically into text. These are the words that the user said. It's a little bit more complex than that, and we will go back to that later. Then the second component takes care of understanding what do these words mean? What's the meaning of this user's utterance? This can be very simple. It can be even combined to the speech recognition, or it can be very complex, depending on what the functionality of the application is. Then we have dialogue management, and this is the component which decides basically what the system will do based on the input it received. Will the system answer the user's question? What information need to be retrieved, and or will the system ask another question, and so on. So where does the dialogue go next? And this part usually is then using some sort of database or another information source to actually provide the relevant information to the user. Then we have natural language generation. So, okay, the dialogue manager now has received some information and decides that this information must be told to the user. Then natural language generation turns that information basically to text. So these are the words. This is the sequence of words that the system should now speak. Of course, there can be some additional information in there indicating, okay, that this is the important part. Do put some stress on this word because this is the important word, and things like that. And then this text, possibly with this markup, goes with the speech synthesis, which turns the text into actual speech sound, and then this is played out loud using the output device. So this is the basic loop. We will look a little bit more in detail these two, and then I think in the following slides I have a few words about others as well. So speech recognition receives the speech and basically returns text, but recognizing the speech is kind of making a good guess, because speech varies so much that the computer cannot be 100% certain what the user said. So usually you actually get out so-called n-best list. So the speech recognizer returns one or more entries. Okay, the user probably said this, but she might have said this or this or this or this. And the more complex language and more free-form language the system understands, the more likely there is this list of candidates. And for all of these, there is also a confidence score that, okay, system might be very confident that this first option is the correct one, but with very low confidence, it might have guessed that, okay, it's the second one. Or it might be that, okay, this is the recognizer thing is the most likely one, but it's very uncertain if that was the correct one. And then there might be some other options. So these can be used by the dialog manager to decide, for example, if it wants to ask a confirmation question that do you really want to quit the system or something like that. And there's some sort of language model which defines what sort of language the recognizer can understand. So there is always some sort of a set of words that the system can understand, and then also how those words can be combined. And these can be defined when we have very clearly defined dialogue, like the system is asking a yes/no question. Then we can pretty much assume that, okay, user will respond with some of these words. Okay, if you ask a yes/no question, the naive assumption might be that the user answers either as yes or no. But of course, there are lots of different options. Like user can say, yeah, sure, correct. No, I didn't say that, or no, I don't want to do that, and so on. So even in the simple questions, it tends to be kind of a more complex case than that, but still, in these cases and this kind of systems, these handmade context-free grammars can often be used so that the developer actually types in these rules stating that, okay, this kind of combinations are possible. Other approach commonly used is statistical models, for example, these n-grams, which basically just tell that, okay, if the previous two words were this word, then the probabilities of the words following it are these, and then basically all the possible words, probability for all the possible words are given that, okay, it's 1% chance that is this word and 0.1% that this word might come now, and then very low probabilities from some others. And these kind of statistical models are basically built by, well, based on some data, so some text or some typed in or transcribed speech is given, and then using a simple or more complex calculation, then these models are created. And these can, of course, because computers can calculate very big models like this, when you give lots of data, these then can handle much larger or more flexible language. So, for example, dictation systems where you can basically say anything to the system, or like Google search, for example, these of course need this kind of statistical model. And of course, Google, for example, is in the position that they have lots of data. So for them, it's quite easy to build these kind of statistical models. Yeah, the natural language from understanding or speech interpretation model extracts the meaning from the text into some sort of form, and whatever that form is very application specific usually. And there are different approaches to this, and this robust parsing is one important aspect, so that because speech recognition can make errors, we cannot assume that, okay, and especially since speech is much less well-formed, let's say, than written language, we cannot, for example, assume that the user speaks grammatically correct language. So because of that, we cannot use some of the methods that have been created for analyzing this perfect language. And because speech recognition errors can make mistakes, miss some words, or replace them with other words. Usually this component should be robust, so that if there is one word missing and one word replaced, it would still find most of the meaning that is left in the utterance. And if there is some insignificant word that goes wrong, then usually the system can still behave correctly. So dialogue management decides what the system will do. Will it answer the question, ask another question, give some sort of confirmation, and so on. And here later I will talk about this initiative a little bit more, but it decides who has the initiative. So if the system is asking questions from the user, or just answering the user's questions and replying to his or her commands. And there will be a few words about the dialogue control models, how this can be actually implemented inside the system. Yeah, output generation, so this natural language generation. When the system knows what it should communicate to the user, this basically turns that into a sequence of words. And a couple of major phases are often identified when this is implemented in more complex manner. Of course, in many cases, this is done in very simple manner. The designer has just typed in that, okay, this is the sequence, and then there may be just some empty slots to fill the values into. But if it's created in more advanced manner, then there can be two steps. One is to decide exactly what information to say, and the second one is to actually putting that into words, selecting what exact words to use, what exact order to put them into. And in this part, if we have a multimodal output, this component can also decide not just what the system says, but for example, what it displays on screen, or like in this Amazon Echo, which is this small device, it has lights on top. It can decide how those lights are used to communicate information and so on. And this is very important part of the design, because if the system output, system utterances are something that are hard for the user to follow or understand, or are misleading, then the user have hard time using the system. Here is just an example from one of our systems we built in the last millennium. Old example. It just shows that often in what this natural language generation generates, it's not just text, but there is this markup. For example, here are information that the speech synthesis, which is the next component, should put some pauses into the utterance so that it's easier for the user to understand. And then the speech synthesis turns this into actual speech. These are readily available technology. Basically, out of the box, you put in text and it provides you speech, and possibly with the some markup to control some of the things like pauses and emphasis. One word here is prosody. So in speech all the time, there are lots more than just the words. When I'm speaking to you, there are lots of information and lots of content, not just a sequence of words. I put emphasis on some words, I keep pauses, sometimes intentionally, sometimes I regret later that I kept those pauses, or couldn't find the words. There is the tone, which indicates, for example, usually when I'm about to end a sentence. Of course, there are things like if I ask a question, you can probably hear that that something is a question or something is an answer because of how the tone of the voice goes. So all these kind of elements are called this prosody. And of course, without the prosody, speech would be very, very monotonous and very hard to understand. So with this markup, the prosody can be controlled to some extent, but speech recognizers also add basic tonal patterns and some minor emphasis into the speech to make it natural and so on. But of course, basic speech synthesis cannot understand what's the actual meaning of the utterance and especially meaning in the bigger context of the dialogue. So it cannot, for example, know where to put the emphasis in many cases. So it must be helped. Multilinguality is still something that is missing from the speech synthesizers, at least in most cases. So if you need to speak in multiple languages, you probably just need to use multiple synthesizers. Yeah, usually you need some sort of application backend, of course, for the database or something, and then this input-output devices. And user systems might have some sort of user model and context model, and if it's multimodal interaction components related to other modalities and so on. So next, a look into the language and speech recognition. Here is a model of how language is often seen in well, lots of different kinds of sciences, or basically these all boxes are kind of fields of science in their own. On the very low level, speech is sound. It's an acoustic signal, usually traveling through air. Then there is this articulatory level, meaning how do we form the sound? How does our mouth and also lungs and so on work to form these sounds? Then we have this phonemic layer. So phoneme is the smallest sound in the speech, which can alter the difference basically. So when you switch from one sound to another, if that switch can switch the meaning of the word, then that's a phoneme. So for example, in Finnish language and also in English, we have like S and T, and I think you can easily think of examples. If you replace S with a T, you change the meaning, obviously. But the different versions of S, sh, they don't change the difference. Tis, tish. They sound maybe funny, but they still have the same meaning. But if you start speaking Russian, suddenly those different sounds have different meaning. So different languages have different phonemes and so on. That's the phonemic layer. So what are the smallest sounds that have some sort of meaning? Then we have the lexical layer, so basically the words, how those sounds can be combined to make words, and what sort of words there are. And then we have syntactic layer, which defines how the words can be combined one and after another to make meaningful sentences. Then we have the semantic layer, which means what the words actually mean. What is the meaning of each word? And in each situation, of course, this, well, that's the second level then. So this, if we just look individual words and their meanings, we're talking about semantics. Then we start talking about pragmatics when we consider the kind of context where the words are. In different situations, the words can have, well, of course, word can have different meanings, and then in different situations, those meanings can be the relevant ones and so on. And then we have the discourse layer. So we have this bigger dialogue and bigger interaction, and of course that alters how we use language and how we interpret that language. So, for example, the irony and so on, you can only understand those if you work on those highest levels. So you must understand the context and the whole situation, that okay, this is the situation where somebody might use irony, and this is somebody who is ironic person. So only after that you might be able to tell that okay, the meaning is actually kind of the opposite of what they are saying. And yeah, speech recognition and speech technologies kind of work on these lower layers, and then the applications must consider to extent of these higher levels. So the core speech technologies in this case are basically speech recognition and speech synthesis, and yeah, dialogue management and this natural language generation are then on this, and understanding are on these higher levels. So yeah, the lowest level speech is sound, and our vocal tract and mouth creates that sound and ears hear that. From the speech recognition point of view, for the computer, speech is, of course, it's sound, changes in air pressure. This is digitalized, well, first turned into electric signal, big microphone, and then digitalized. Then actually how the speech recognition works is takes this waveform of sound and splits it into small segments, usually 10 to 30 milliseconds, very short segments. And then these are analyzed into features. So basically this 20 milliseconds of sound is turned into something like 30 features. Features are numbers basically, and what these features are, it can depend, and this is kind of one of the fields where there's lots of research still going on and has been over the years. What features are the best for speech recognition? So this larger amount of data is tried to convert into these features, smaller amount of numbers which have more meaning, which are closer to speech. So there are kind of like different frequencies and relations of different frequencies in the sound. And the actual features used for speech recognition rely very much on the fact that it's speech that we are trying to understand, not some other generic noise or other sounds. And then when you have this list of these features or coming in, then this is compared to some sort of statistical model of the language, and this combines the vocabulary, the words that there are, and then the grammar level thing, how these words can be combined. Hidden Markov models were used for a long time and are still very common in speech recognizers as the statistical model, and lately this deep learning based neural networks have been increasingly used for this kind of statistical modeling, and then this process returns this n-best list or some other structure which provides the information that okay, that user probably said this, the sound that was provided to me was probably caused by the user speaking these words. This is kind of from the mathematical point of view, what is the problem of speech recognition or how it's considered. This is a picture of the same thing. So we convert the sound to digital and then into features. And then here you can see two models. So feature models and structural models. These are, in this case, in this following slides called acoustic model and language model. And yeah, I go to this now. So the acoustic model basically tells how the different sounds, how the different phonemes sound like, or basically phonemes in context and so on. So acoustic model tells what the language sounds like, and it's basically created with kind of statistical or machine learning tools from large collection of example speech. So when a speech recognizer is created, usually there's hundreds of hours of speech with carefully marked that, okay, this is what was said in this case, and these are the different sounds and so on. And based on these, for each different sound in the different context, this acoustic model is created. So this model tells how the language sounds like, and of course, to get good model, you must have good sample of different kind of speakers, both genders, people of different ages. If you want to support different dialects, you must include people from those dialects. And of course, if you just create a model for one single dialect, you might get better results from speakers of that dialect, but then not from others. And most of us, for example, speak English as a second or third or whatever language, and we don't sound like native speakers. And there have been some, and I think Google, for example, is including lots of non-native speakers in their language models, for example. And this also includes effects like the quality of the incoming sound. So when lots of systems were created for telephone lines, then they used audio that was recorded on telephone quality, but now what most of the system use a higher quality input. They try to get as close as possible to the correct kind of microphone and everything like that. And in the correct kind of environment, if the application is used in very quiet environment, or if it's used in very noisy environment, you might want to have different acoustic models. Yeah. Then you have the vocabulary, which is basically part of then the language model. So this is the set of words that the system understands, and of course it must include information what are actually the sounds that make these words. So for some languages, like Finnish language, it's almost trivial to convert the letters in word to a sequence of sounds, sequence of phonemes. There are only a couple of exceptions where the single letter doesn't map into a single phoneme. But in English language, for example, we have lots more variation. You must know the language reasonably well to know how different words are pronounced. If you see some word you haven't ever heard, you might actually pronounce it wrong. In most cases, you can deduct that, but not in every cases. And then, of course, there are France is a little bit even more extreme in this sense. And then there are, of course, different kinds of languages like Chinese. If you're using those kanji signs, then you must have lots of information or basically knowledge. And I think there's also a little bit of context dependent, and the different versions of Chinese, of course, with the same characters, you can have different sounds depending on which Chinese you are talking and so on. And then we have the language model, which defines the structure of the possible sentences, how the words can be combined. And here also, as I said, it can be based on some handwritten rules or statistical models. So you take 1 million words of text and create statistical model out of that. Some problems have come out of that also because, as said, spoken language is not the same as written language. So if you take 1 million pages of newspaper text, you end up with quite different model than what people actually use if they just casually talk to each other. And yeah, you have those features, and then some kind of statistical model is used to compare the list of features or set of features you get from the sound to this language model, and then you get the most likely reason why this sound was made, meaning this is the most likely thing the user said. Quickly, this concept of perplexity is a term that tells how complex the language model is. So as said, if you have a very simple case, you know that, okay, we now ask user a yes-no question. Well, the extreme case is that we force user to say either yes or no. Then our perplexity is basically there are two options which the user can say. But if we think of just supporting so system where the user can dictate anything, then you basically can have massive different branches where the user can follow things. Of course, there are situations where that we know that, okay, this word and this word were said previously, and then the next word, we can kind of rule out lots of different words, but still there are lots of different options there. So perplexity is kind of the average of the different branches where what the next word could be over the whole thing. And this, of course, indicates how hard this problem is. If we know that user will say either yes or no, it's quite easy problem, and the computer can very reliably tell whether the user said yes or if the user said no. But if we allow the user to say anything, just start dictating any text, it's much harder problem, because we have to potentially we have lots of different options to look out and try to find the most likely one. Yeah, so if we have this simple grammar, small vocabulary, low perplexity, recognition can be accurate and fast. And but then the problem is that if it's too limited, the user can very easily say something that is not included in our grammar or language model. And what then happens depends very much on the speech recognizer and language model and the situation. Sometimes, if we are lucky, the speech recognizer rejects that, okay, the user said something that's not in my language model, or it returns that, okay, user most likely said this one, but I give it very low confidence because it didn't seem like that. But in many cases, speech recognizer actually returns something that sounds somewhat similar to what the user said, but can be found in the language model and gives reasonably good confidence score as well. So in this case, the system has very hard time, or it might be impossible for the system to know that, okay, the user actually said something that it doesn't even understand. And these are very hard things to handle. And then if we have complex grammar and large vocabulary, then more likely there are similar sounding options. We get longer n-best list, the entries might be in the wrong order, all kinds of errors increase, recognition might be slower, of course. Well, nowadays we have lots of computing power even in our mobile devices, so it's not so much issue anymore. But less likely that the user says something that's not in the vocabulary. Alternative option is this word spotting, which is rarely used today, but it's basically systems where the computer listens to all the speech, but then only listens to certain phrases and then rejects or ignores everything else, but only reports that, hey, now I heard that thing, and now I heard that thing. Well, there is one case where that's used, I guess, quite commonly nowadays. So, for example, in the Android phones, you can have activated this OK Google, and now it, well, voice OS like what has been, but yeah. So it all the time it's, well, almost all the time listening to the one keyword. So that's maybe the only example of that which is commonly used. But yeah, it never really caught up, this word spotting thing. I don't think I will go through this example of what sort of handwritten grammar there could be. But yeah, speech recognition is hard because speech varies so much, and there are lots of things that can vary in there. Linguistic variations, because the language varies between people and so on, and the same sounds sound different when they are spoken in different parts of the sentence, for example. So same sound in the first sound of the sentence sounds actually quite different than if it's the last sound of the sentence. Acoustic variations are quite massive. So if I'm speaking here and the microphone is listening to me, it's quite different than if I'm walking outside and there is some wind and I'm further away from the microphone and so on. This room has some echo, for example, and a little bit of background noise and lots of variations like that. And then, of course, everybody has different voice. We all sound different, and also we sound different at different times. When you've just woken up in the morning, you might say sound quite different from midday. And then natural speech contains, as you can hear in my speech, especially if you start listening to those, lots of hesitations, false starts, repairs, breaks, and sort of ungrammatical stuff. And all this, to some extent, needs to be handled in these systems. Yeah, here are just a couple of categorizations. So we can have vocabularies of different sizes. Our language model can just be a set of different phrases, just yes or no, or we can have rule-based system or statistical big language model. We might be able to just change the language model between one language model and another. We might be able to create, based on the situation, a new language model. For example, if we know the user's name, we might add that name into that language model. If we have these large statistical language models, of course, it's changing. It's very hard because you need to collect a new set of data and do a lot of this number crushing, so that can be hard. Early on, the very first speech recognizer were speaker dependent, so every speaker had their own acoustic model, and if I spoke to the system, it understood me. It probably wouldn't have worked very well for, well, maybe one or two of you would probably have a good system for that. Nowadays, some of the systems are adaptive, so especially dictation type systems, the more you speak to the system, the better it starts understanding you, because it's all the time collecting your speech and kind of correcting its acoustic model, and to extend also the language model to match the way you speak. Or it can be speaker independent, like by default, most of the systems nowadays are that anybody can come and talk to the same system. Very early systems also had this discrete speaking style, so you actually had to have pause between every word. And well, actually, not everybody has understood that in natural speech, there are no pauses between words. If you record your own speech or my speech and look at the sound, for example, in sound editor, there are absolutely no pauses between the words. There are no clear indications that, okay, one word stops here and another one starts here. You must actually understand the language to be able to tell that which is the start and end of each word. So, of course, continuous speech is what modern speech recognizers support. The next step is actually supporting spontaneous speech. So, as said, well, it's still one thing for me to carefully think of what I will say and then say that thing and then just speak out something that comes to my mind and not really think about it. And this kind of language is more unpredictable. Then in dialogue systems, half-duplex is system where you speak and then you must wait for the system to speak to you, and only after the system has spoken, then it starts to listen to you again. Parts refers to the fact that you can speak over the system and then it will hear that, okay, now the user is speaking and stop itself. And then full duplex is that what we have between human beings, that both of them people can be speaking at the same time. And then environment, of course, we can have very quiet environment, normal office setting and hostile setting, for example, in the industry or in some working vehicles and so on. We can have very noisy conditions, and these are, of course, quite hard. But as said, there are some examples of speech recognition with small vocabulary can actually outperform human beings in these very, very hostile environments. And then the sound quality, microphone quality, and so on, they can be different. Okay, a few words about speech synthesis. they convert text to speech usually. So the text to speech is very common name for speech synthesizers. There are different approaches to this. Concatenative synthesis basically takes parts of recorded speech. Some voice talent has been in recording studio and recorded lots of speech, and then that has been segmented into small segments, and then concatenative synthesis takes those segments and glues them together to create speech. Formant synthesis, on the other hand, is simple model of how speech is formed. So it creates the basic waveform and then adds some filters and adjust those filter parameters to create speech. These are the traditional computer voices that you have heard in, well, old movies at least. Kind of traditional, quite unnatural, but it's possible with very little processor power and very little memory and so on. Articulatory synthesis is basically full model of the human vocal tract. These are used only in research because they modeling the whole thing, actually what physically happens in our mouths and so on, is so complex that the speech quality of this system is not as good as this concatenative synthesis. But it's very heavy processing, so it's good for some scientific research to understand how our speech system works and so on. And we can have a plain recorded speech, which in some cases is very good. We can have some celebrity voice reading all the utterances and have very lively output and so on. But of course, this is not then flexible at all. So concatenative synthesis is the kind of the standard. Most of the speech synthesizers use this one. Some sort of segments, units of speech are selected from the recorded material, and then these are assembled together. And prosodic information is included after or during this concatenation process. So meaning that, for example, the tone of the voice, the pitch can be altered to some extent by adjusting how fast the sound is played back. And then there are lots of work required to make it sound natural. So the modern synthesizers, they have lots and lots of like hours of this recorded speech, and they try to find the best segments to not just thinking to locally, okay, that these are the sounds I must make, but also it's part of this kind of sentence in this location, and they use as long segments as possible and try to find really the best combination there. Requires lots of storage, quite a lot of computational powers. This might have like a gigabyte of audio where the sound is created from. Lots of research has been going into and is going still into how to choose these units, how short or long segments we should use, and what rules to use to combine these together to get the prosody and so on in there. The unit size can be these phonemes or syllables or words, and this co-articulation is the challenge because, as said, different or same sound can be actually very different depending on the context. What are the previous sound, next sound, what part of the sentence it is, and so on. So yeah, like these diphones and triphones. So the segment between two phonemes, for example, or one phoneme in the context of two phonemes or half syllables are often used. And this co-articulation refers to the fact that the sounds are different depending on what's around them. So co-articulation. And yeah, it's hard work trying to make all those problems disappear that are there when you glue these separate segments together. There are just some calculations. So if you use different kinds of units, you need increasingly more material the longer the units are because there are more combinations. And as said, the The unit selection synthesis is the name of the modern approach where you have different lengths of units and you are choosing the best ones available depending on what the text that you are synthesizing are. Format synthesis, as said, is this very basic model and doesn't sound natural, but it can be easy to understand still, and the prosody can be fully controlled because it's built on such basic process. And the articulary model, as said, is very complex and mostly used for research. Yeah, a couple of technical aspects, and but basically speech synthesis is something that you have readily available. Lots of different manufacturers have speech synthesizers, and like operating systems include by default speech synthesizers, and readily available technology. Of course, there are some challenges, and one of these is this text normalization. So here is an example of how to read this text. So I guess the correct one is Dr. Jones lives on Palm Drive. But both of these DRs are pronounced very differently, and to be able to tell how to pronounce those, you must understand quite a lot about the language. And also like different numbers and so on, like well, in the GPS or navigation systems, I think we heard, I heard a couple of days ago example of where Google is reading the street name or road name, which is a sequence of numbers, and then it's actually putting that into a correct word form in Finnish, and it's kind of making it mistake and saying something very silly that's boring to listen to and hard to understand. And there are lots of different things, like how you pronounce web addresses. People do that differently, and depending on the situation, can do that differently. So it's not a trivial problem. There is some possibilities for control, volume, speed, some pitch variations, emphasis, pauses. Emotion is kind of an aspect of its own, but some synthesizers allow you to add some emotion, like surprise or something like that, in basically with special phrases. And as I said, if there is no prosody, it's not good speech. Basic prosody is added by default, and then you can use tags to add more. Recorded speech is, of course, kind of the ultimate quality if you have a good speaker. If you have an amateur speaker, you probably have something worse than an average text-to-speech synthesizer. But if you have a good actor reading things out loud, you can get a very good quality, but of course then it's very limited amount of phrases because everything must be recorded, and preferably everything should be recorded in one session. If you have the same person coming back next week, they might actually sound significantly different, so that the users can hear the difference, because whatever they have done in the previous night, for example, might have changed their sound a little bit. And there are some tricks on how you can glue words together, how to pronounce them, so that if you glue some words inside the sentence, for example, how to make it sound continuous. Basically, every word should be pronounced in the correct context. Okay, then to the interaction part. First, dialogue management strategies. There are two sides. How the dialogue goes from the point of view of the dialogue itself. And then second is the control model, how that is actually implemented inside the system. So the initiative is the most critical part of this first part, how the dialogue sounds like, or how it's formed. Let's use that word. So basic types, one is system initiative. System initiative basically means that the system is asking questions from the user. And this can be good strategy in some situations where we have clear task. The system must know this information, and then it can do the thing. But of course, then it must also ask some sort of confirmations usually, because if there is a speech recognition error and it's just the system asking questions from the user, then the user doesn't have any way to correct them unless the system asks some sort of confirmation that is this correct. I won't go through these examples. You can find the slides in Moodle and have a look at them. System initiative, of course, creates very predictable system. That's quite easy to the user. The user is just answering the questions. If the questions are well formed so that the user knows how to answer them, it's easy for the user. And usually the natural language understanding is also simple, because we know what we ask, then we know how to interpret what the user said. Extreme cases, we are just asking yes/no questions. And yeah, of course, this requires also that we know what we need to do. We have a clear goal. It's easy for the user, and like user using the system the first time can probably feel quite reliable that they know what's going on. But for experienced user, it gets really boring. You're just answering the questions and then waiting for the next question. And especially if you know what the next question will be, and then if there are no possibility to barge in and stop the system, it can be really boring. But then it can be made a little bit more flexible so that you can, for example, provide also the next bit of information in the first answer. So if it's a ticket reservation system, where you are going from Tampere, where you are going to Helsinki. Next time you go there, where are you going from Tampere to Helsinki? So if you have smart enough system, then it can skip the second question. Yeah, suitable only if you know exactly what the structure of the task. More open-ended systems are not possible. And of course, we don't need to build the entire system using just one strategy. This is good, for example, in error correction or some subsegments of the dialogue, but then we can have other parts using this different approach, which is user initiative, basically, which means that the user is in control of the system. And basic example of this is this kind of command and control. User is giving commands to the system, and system is reacting. And of course, for experienced users, this can be very efficient, and more open-ended systems can be implemented in this way. But then, of course, the user must know and understand what is possible with the system. So they must learn it somehow, maybe with some tutorial mode or something. And this can then, of course, use the benefits of the natural language so that user can efficiently express lots of information if the system is advanced enough to understand that. But yeah, our language model must also match the flexibility we want to support. And the user must understand still what are the limitations of the system, what are the things that the system can provide you answers with, or what are the tasks it can do for you. Here are some examples. So, of course, in real life, we mix these two and we end up with something called mixed initiative dialogue management. Part of the dialogue is user initiative, part of the dialogue is system initiative. And yeah, there are some findings from earlier systems. So you can, of course, have more efficiency when you allow this flexibility, but system initiative can be easy for the users who are using the system for the first time. And yeah, basically things that I said already. And of course, this can happen differently, so that we can either have a system where some parts of the interaction are strictly user initiative and some part are system initiative, or we might allow full flexibility so that the system starts by being system initiative, but the user can take the initiative at any time. Instead of answering the system's command, the user can, or use system's question, the user can give some command or tell the system to do something. In extreme cases, the system can hopefully adapt to each user and the style they want to use for the interaction. Yeah, and error correction is basically where the system initiative can often be utilized, or should often be utilized, so that if we know that, okay, some error has happened, for example, the user has said, no, that's not correct, then we might switch to system initiative and start asking questions one by one. Is it Tampere where you are going from? Please say yes or no. Is it Helsinki you are going to? Please say yes or no. Kind of extreme case of switching to system initiative error handling to make sure that, okay, we get the correct result. Yeah, and you can mix these in different ways with more successful or less successful manner, basically. Some samples. Then how you can handle or actually implement the dialogue control in the system from technical point of view. One very simple model is state machine. So basically the system is just modeled as a sequence or set of states, and then there are transitions from one state to another. And basically in each state, system says something, and then when the user says something, that what the user said specifies where we are going into this state machine. And this is, well, matches very well for the system initiative strategy. But of course, it's not very flexible, or if you try to make it very flexible, you end up with very, very complex state machine where, well, then you definitely don't want to manually write that sort of state machine to model the system. Because the state machine approach is something used often in software development. In the dialogue system, it can be easy model to understand, and also if you do the very basic state machine based modeling, you can also switch the recognition grammar on each state, so that you know that, okay, in this state I'm asking yes no question, then I'm using the yes no grammar, and then I'm going to this question where I am asking the location of where the user is going to the train, and then I use a different grammar, and so on. And yeah, usually you add something, some sort of variables and something into the state machine. Don't use the pure state machine, but also the states can encode some of the information in the dialogue. As said, with basic state machine, it's hard to implement some real-life cases. For example, the error correction gets very complex, so usually there are some sort of extensions like sub-dialogue, so you can go to sub-dialogue and jump back to the state you were, and so on. And maybe some global things that are available all the time. This is suitable for well-formed simple tasks. And yeah, bigger systems, the state machine basically exposed to be so complex that at least manually writing is not probably a good idea. Of course, you can still use the state machine approach behind the scenes, but you define the dialogue in some higher level system and then use some sort of compiler to actually create the state machine and run that in the background. Another approach is this frame-based or templates. So basically this kind of form-filling approach. All the time the system is trying to fill in some form. There are some slots of information the system wants to get from the user. And then you have some sort of algorithm which decides on the state of the form what to do. If it's an empty form, there might be some default question. Then user answers something. One or more items in the form might be filled. If then only one item is missing, then probably the system will want to ask a question to fill that particular item. If it's a big form and only one item gets filled, the system might decide just go to the next, ask the next item, or ask a bigger question to ask for multiple items and so on. So these allow more mixed initiative dialogue by default and more flexible dialogue flow, more efficient interaction because the user can, or they can naturally model the fact that user fills in lots of the slots in one utterance. But of course, just basic approach fails in some cases, like there might be that if this value is built into this slot, then this slot is no more relevant and so on. And this kind of approaches break the very basic frame or form filling approach, but then you need some sort of extensions. Yeah, and these two approaches are implemented. For example, there is this markup language called voice XML, which can be used to model spoken dialogues. And there are a couple of different software implementations where you can then run this, for example, to create these telephony systems. And it actually mixes these two approaches. So you define these forms to collect items of information, and then when a form is filled, then you transition to another state which has its own form and so on. So this kind of combination of state changes and form filling then allows you to create quite flexibly different kinds of combinations. It also has scripting similarity to HTML. So ECMAScript can be used there to script items. So you can do these special cases and control state transitions, for example, more flexibly. Just quickly, some other examples. Agent-based dialogue control is kind of generic name for a couple of different systems, but there the point is that it tries to see both the user and the system as kind of active agents trying to fulfill some goal, together solve some task. There are other approaches mentioned here: event-based systems, collaborative agents, theorem proving systems, dialogue description languages. Well, basically voice XML is one kind of dialogue description language. And yeah, how to select an approach? Well, basically it depends to great extent what sort of other platform you have in there, but then also what you are building. So state-based is good way to model simple and very strict dialogues, and frame-based is good when basically you want to get multiple items of information. And then as the last topic, in the last couple of minutes, error management. So as said, speech recognition especially makes errors, and even if we had the perfect speech recognition, the user might still make errors, accidentally say the wrong words or something like that. But by default, we must assume that our speech recognizer makes every now and then errors. And of course, these are problematic. and some sort of error handling is needed to make sure that the system doesn't make the wrong things based on when these errors happen. Poor error handling can just make things worse and lead into these error spirals. So the user is trying to fix the previous error and another error happens, and then they are in even bigger trouble. Speech recognizer can make different kinds of errors. Rejection is that recognizer just rejects the speech. It doesn't notice that, okay, this is speech. So it doesn't do anything even if the user says something. Substitutions, insertions, and I think it's actually missing deletions are the basic kinds of errors, so that we get something, but substitution means that one word, for example, was replaced with some another word. One word was mistakenly recognized as something else. Insertion is that we have what the user said, but we have some additional word somewhere in between. And deletion is that we are missing one word from there. Word error rate is the kind of standard measurement. Basically just taking these different kinds of errors and dividing it by the number of all the words that the user said. And if all the words were incorrect, then you get 100% error rate. And if everything was correct, you get 0% error rate and something between there. Of course, the natural language understanding can also misunderstand what the user meant with what they said. And then there can be this kind of semantic error. User says something that is actually not possible in that situation. The user might be confused. They might have misheard something, or the system is just working in illogical way. Well, this is another categorization of what sort of errors we might have error situations. One is that we don't get any input. User isn't saying something when we are assuming that, okay, now the user should say something. And of course, we need to handle that somehow. We might have recognition rejection. So the recognizer tells that, okay, I have no idea what the user said. I cannot give you any assumption, or I think I don't know what this is. Then we might have a situation where the recognizer returns something that cannot be understood by the natural language understanding, or something that is not semantically consistent so that the system can understand it, but okay, it doesn't make sense one way or another. User wants to buy a train ticket to the waiting room in the railway station. That doesn't make sense. Then it might be that, okay, it looks like sensible thing, but the system cannot do that action. And this might be because of the external factors or because where the dialogue is. So these are considered two different things. And then the backend system fails, the database returns that the computer says no. And then the last level is that the user initiates the error correction. So it says that, okay, this is wrong. And these are the type of errors that the system can somehow detect that, okay, now something is wrong. And by the side of these, there are those errors where the system doesn't know that something went wrong. And this is something that you must remember, that, okay, if there was an insertion error or deletion error in the speech recognition, in many cases, the system has no idea, no way of knowing that, okay, something went wrong. And because of this, we must have confirmations in the dialogue. So detecting these errors, those previously listed cases are where we can detect that there are some cases, but in most cases we cannot at least certainly say that, okay, there was something wrong. Confidence scores can sometimes help we can think that, okay, probably there was an error, and then we can ask confirmation, for example. But often, for example, substitutions lead to something that looks perfectly fine to the system, and the system has no way of knowing that, okay, an error has happened. And yeah, it's easy to forget all these situations when you are designing a dialogue system and thinking about the errors that, okay, the system, you cannot know that there was an error. So because of this, the system must communicate what it has heard, how it has understood the user's input. So basically confirmations, and there are some examples in there. There is overly complex model we at some point decided to write what can be the stages, error detection, then you can diagnose and plan the error correction and do the error correction and close the error correction and then try to prevent future errors and so on. But yeah, so how you manage the errors, you can do confirmations, you ask confirmation from the user that is this what you want to do? And using the different kinds of information like the confidence scores, you can give the confirmation more often or less often. For example, so if you have low confidence score, you can confirm immediately, but if everything seems to be going very well all the time, you do only one confirmation in the very end. You can do this confirmation by yes, no questions, or switch to yes, no questions for the whole dialogue. You can ask the user to rephrase or re-speak what they said if it was, for example, rejected. Spelling is kind of extreme case of if some input is not understood. You can list the options for user to choose from if to make sure that the user knows exactly what to say. And of course, multimodal means can be used for error correction. So if you have, for example, in a car a touch screen, then you can just display that, okay, did you want this or did you want that on the touch screen? And that's kind of more secure way to doing it. And confirmations, they can be explicit. Are you sure you want to quit? Please say yes or no. Or they can be implicit. Destination Hervanta, what time you are leaving? So when we are asking the next question, we can already say what we understood as the previous question, but we don't explicitly tell the user that is this correct. We're just telling that, okay, we understood that you are going to Hervanta, what time you are leaving, and then if the user said that no, I'm not going to Hervanta, I want to go to Kaukajärvi. Of course, this can be a little bit confusing depending on the system to the user to what is exactly, what should they say if things are wrong. But this implicit confirmation can help the dialogue flow and continue forward. So if everything goes well, it's efficient and more lightweight. But you can still overuse that if you just add it to the every phrase. And slightly over time, that was my last slide. Yes, I hope everybody has a paper for the paper presentation by now. If not, come talk to me. And next week, we will talk about the very first exercise. So for the first exercise, you need to post for the next week's meeting your first analysis of the paper that you are writing. So do that, and we will have a more discussion type meeting next week. And there is a design exercise for speech. So have a look at the Moodle for the exercise and start doing that. And remember that you have 2 deadlines for the design exercises. First, you must post the title of your design into the Moodle, and then in the final deadline, then you must post the actual presentation of your design. So remember to do both of those. Okay, thank you for your time. See you next week.